Good morning, AP Physics. Trucking right along with the review. You should be good to go if you are watching all these videos. I mean, obviously, just let me know if there's something you feel like you need that we're not doing, that you have questions about, that you feel like I'm just leaving out of the overall subjects, that kind of stuff. Remember that you can go back and look at any of the FRQs we did previously. Hopefully you remember how we solved those. So yeah, you should have a good background. We're going to start with circular motion today, and we're going to go through that. You can see these movies have been taking me around 22 to 25 minutes to go through an entire subject. Yeah, so I'm going to get directly into it, and yeah. You may notice that I do have a picture of Brevard County behind me there. My mother-in-law and my father-in-law were both long-term postal workers. They retired from the post office, and so they have this old postal map of Brevard County that has a bunch of towns on there and stuff that don't exist anymore, which is kind of cool. Yeah. So let's talk about circular motion. Now, I just edited something out. It was a waste of your time, don't worry. So with circular motion, we want to go back to dynamics. In the dynamics, we had Newton's 3 laws, and in this case, we're actually going to use all of Newton's 3 laws in this chapter again, but in circular motion, right? With how does it impact something moving in a circle? So going back to Newton's first law, we know that something, if it's moving in a circle, has to be doing so because there's an unbalanced force, right? Newton's first law tells us if there are no unbalanced forces, then an object will go in a straight line at constant velocity. Going in a straight line is constant velocity because turning again is a change in velocity. And that is, in this case, the first thought we want to think of for everything else in the chapter is, when we go in a circle here, most of our things are going at a constant speed, right? But the component of their velocity that's changing is direction. Remember that acceleration is a change in velocity over a change in time. And we know that that's literal, right? There's an actual formula. Acceleration is literally delta v over delta t. So in this case, the thing that is changing with our velocity is its direction. And so we're going to go in this circle with this unbalanced force, right? And Newton's first law again tells us that. So just taking a look at a circle again. So zoom, 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 zoom. All right. Looking at these forces. So let's look at this first example, right? So I am going in a straight line when I first start moving, and then I go along this curve. Either way, you can see either way direction I'm going, I still straighten out. Ideally, we're talking about going from the top to the page, going towards the bottom here. But when we go to turn, you can see we have this unbalanced force. So up above, I could be accelerating. I don't necessarily have to be at equilibrium, but that unbalanced force must be in the direction that I'm traveling, right? It's either going to be in the direction I'm going forward or in the direction I'm going backwards. Now, here, this direction, this unbalanced force is going to be perpendicular to that motion, right? And so in this case, we can tell that this is going to be in. You can see that arrow is pointing into that inside the radius of that circle there, sorry. And that's again because Newton's first law says that if we are turning, there's an unbalanced force in the direction of that turn's radius, right? So again, if I'm turning to the left, there must be something pushing me in that direction. In this case, let's say that this was like a car, right? So if a car was coming down the road here and it was going to make this turn, right? And I know that I'm looking at it from this side. When it comes along here, what's going to happen is there must be some force from the outside of the car causing it to not go in a straight line, right? So in this case, we know that if there were no friction, this car is going to go in a straight line. And that's what Newton's law tells us, right? If there's no unbalanced force, in this case, something that would be provided by that friction, that this thing is going to want to go in a straight line. That's what happens when you lose friction on with your tires. So if you are on ice or water, or if you're just going really fast and you go to turn and your car can't do that, it will just go in a straight line. Some of them tip over, and that's to do with like center of mass and that kind of stuff. But like, let's just say that it was like a really low car, like a go-kart or something, and you're going really, really fast and you turn. As long as, again, your center of mass isn't such that you'll tip over, you'll just slide and go straight because you no longer have this unbalanced force to make you not go straight. So here, this unbalanced force is got two names, right? We have this force that goes in towards the radius, which we call centripetal or radial force. But remember, that's a general name for whatever force is supplied. It's just telling us what direction that force is, right? Centripetal or radial forces are the direction that they are. In this case, that force is supplied by the friction of the tires. So my centripetal force or my radial force is my friction. I know that's something we had a hard time with earlier in the year, is that naming convention. One just tells me the direction, the other one gives me the title. It's just like previously. Let's say that you were pushing on a box. Yes, if you're the only thing pushing, then you are the net force. But at the same time, you represent a named force there, which that force is going to be the force of your push, or whatever you want to phrase that. So again, we have different labeling conventions. We covered a little bit of that in the last chapter with talking about force up and force down, and how we go back and give those more specific names or titles. Okay? So in this case, again, that car was going down the road, it went to turn, this force, this unbalanced force, is supplied. So when you're in the car, you get this feeling of being thrown outwards toward the outside edge of the car. That's not really what's happening. Again, you want to keep going straight, but the outside edge of the car pushes you in towards this radius, right? So again, you just want to keep going straight there, but the car doesn't let you. And that's essentially, I just erased one of my own things. That's essentially how that would work. So let's talk about this in an actual circle, like a full circle. I just erased one of my little titles here, so I apologize. So again, that's where we're going to get these terms, radial force and radial acceleration. Because if I were going in a complete circle, that force is going to point along my path in towards the radius of that curve. And so that's again why we call it radial force or radial acceleration. Sometimes you'll hear it as centripetal force or centripetal acceleration. I don't really have a preference. I don't mind either of them. They both make sense. Centripetal meaning center-seeking, and in this case we do have a center-seeking force. So again, if I am turning, the overall sum of my forces is a centripetal force in the direction of the center of that curve, right? Because again, you'll hear a lot of things about centrifugal force. Oh, I'm being thrown towards the outside of that car with centrifugal force. Well, no, you're not, right? You're being pushed in towards that curve. That doesn't mean you can't have centrifugal forces, right? Would say that you are going around the outside edge of that curve. Your friend can be in that car and they can push you towards the outside edge of that car. But they can't ever push you hard enough that your overall force is towards the outside edge, because then you'll start to turn. And then you're in the car, you're not going to turn unless they push you through the door, right? So just think about it that way. Again, if you are turning, the force that's making you turn, the overall sum of those forces is going to be a centripetal force. Okay? So let's talk about those definitions. First thing we're going to have is a definition for what is my centripetal acceleration, right? Because force here is actually relatively easy. We have this thing called radial force, but it's the same definition. It's the same definition that we had for my Newton's second law. The sum of my radial forces are equal to my mass times my radial acceleration. That one's really easy. Again, that's the same thing as saying F equals ma, except for now our A has a different definition. Cool? So we have a different definition for our acceleration, and that one is also itself pretty straightforward and easy. It is going to be velocity squared over my radius. That is my radial or my centripetal acceleration. So if a problem were to give me how fast something was going around the outside edge of the curve and how big that curve was, I could figure out what the radius is. And again, provided the mass, I could also go back and figure out what's the actual force on this thing. Now, there may be times where I don't know that, but I am given a force, right? Maybe sometimes they'll tell me what the radial force is, and they want me to solve for the acceleration. So think about it this way. The same kind of example we just had, and I'm going to draw this out. So taking a look at this curve. So same example I just kind of had. Let's say I'm going down the road and I want to turn in towards this curve. I'm sorry if I'm doing that in a weird way. Then I know that I'm going to have this radial force. Well, in this case, I have that directional force, radial force, but what supplies it? Well, it's all going to come from the friction. So let's say that I can solve the friction. They're going to tell me what the normal force on this car is, and they're going to tell me what the mu is. And so I can find out what the frictional force is. Well, I can plug that frictional force in for my radial force, and that will allow me to go back and solve for that acceleration. Now, again, that's given the mass. If they gave me the acceleration, I go back and solve for the mass. So don't forget that, right? We can label these things and make sure that we know what are all the forces that we're experiencing. Now, we can have more than one radial force, right? So let's say that this thing was on an incline, right? Let's say this car was like on a ramp or like a banked turn is a good way to put that. So not only would friction be helping it go around that turn, but you'd also have gravity helping it kind of like stay where it's at on the inside of this turn, because you're going to have this, actually it's not gravity, it's the normal force. That's fine. But the normal, we're only experiencing the normal force due to gravity, which I know is a weird thing. I'm going to cover a bank turn a little bit more in depth a little bit further on, but the idea being that like you can have more than one radial force. If you remember correctly, in those problems we had two. We had this normal force coming off the ramp in towards the circle, and we also had this force of the tires, right? Friction giving us that. So if we were to do that, we would also have, when we had this sum of my radial forces, we would have more than one listed. That's pretty much it. Cool. So we could also use this to solve for the velocity, right? So let's use this same exact example. Let's use this exact same example. There you go. So I wrote this out. So in our last example, I had our radial force as 2.5 newtons. So let's say that they gave me the mass and the radius of that curve. The radius of my curve is going to be 2 meters, and the mass of this object is going to be 1 kilogram. Well, given that I know that my radial acceleration is v squared over r, then I can go back and solve for how fast is this thing going around the outside edge of that curve. So I'm going to plug those numbers in, right? You'll see I plugged my mass in as 1 kilogram, and I put the 2 meters on the bottom of my equation here, right? And I still have velocity squared as my unknown. Now you may be saying, but I thought it was v squared over r. Why is it m times v squared over r? Remember this idea of our cumulative property, it doesn't really matter what order we multiply those numbers in, right? As long as they're all part of one term, all of those operations are going to be done. It doesn't really matter. We can divide both numbers by 2 first and then multiply the numbers. We can multiply the numbers out and then divide the 2 out. It doesn't really matter, right? The idea being that, like, I could take that over 2, pull it out to the front, put the 2 other numbers in a bracket and multiply them, and it really wouldn't matter. That's the thing that some people struggle with, and often have a hard time when I'm doing math, going like, well, why did you do it that way, or why I'm not following along here? Remember, it doesn't really matter. So we have 2.5 newtons is equal to my mass times my velocity squared over my radius. And again, I can go back and I can solve. All right, I'm going to multiply each side by 2 to get rid of my 2 meters on the bottom. So now I have newtons times meters is equal to 1 kilogram times velocity squared. I'm going to divide the 1 kilogram out. Now remember, newtons are kilograms times meters per second squared. So that means that I have to get rid of the kilograms, so I have meters per second squared times meters, which gives me meters squared times second squared. I take the square root, and that is going to give me the square root of 5, which I'm not going to do because I'm going to keep it simple. Meters per second is my velocity. All right. Pretty cool. Well, my opinion, but pretty cool. So that works out. Yeah. Don't forget, we have this alternate expression for our acceleration, right? So we know, or hopefully you know, at this point that we have a new definition for what our velocity is. We have this thing called angular velocity, and it is 2 pi r over t. 2 pi r over t. Now, 2 pi r is because the radius of a circle is 2 pi, and if we multiply it by the radius of the circle, it'll tell us what's that distance. That's the distance that we cover. And then t is the period, or how long does it take for us to cover that distance. So if we take the distance that we're covering over the time that we're covering it, that's going to give us velocity, right? So we have this alternate expression for radial velocity. So we're going to use that, and we can plug that in to give us an alternate expression for radial acceleration. Now you may be saying, well, why do I need an alternate expression? Well, let's say that they're only giving you the rate that something is turning at. They're not giving you its linear speed or its tangential speed. They're not saying it's going 14 meters per second. They're saying the circle is this big, it's completing this cycle every X number of seconds, right? Well, that we can still solve for our radial force just given this other expression. So we're going to take this and plug it in. We have a r is equal to b squared over r, right? And we're just going to plug it in as our velocity because it is. It's just our velocity in a different term. So what we're going to do is square this 2 pi r over t. Because we need to have 2 pi r over t squared. Everything there is inside the parentheses. And that's, again, that's just our velocity squared. And that's going to give us 4 pi squared r squared over t squared. 4 pi r squared over t squared. Now when we plug that back into our radial acceleration formula, one of those r's is going to cancel out. Because it's going to be this entire term, divided by r. And as you can see, that means that we're going to have r squared over r. So that means that if I plug all of that back in, my radial acceleration in terms of angular velocity is, I apologize, give me 1 second. 4 pi squared r over t squared. Radial acceleration is 4 pi r squared, 4 pi squared r over t squared. And again, that's because that r cancels out. The reason why I paused there was not because it was hard for me to plug that back in. It's because I want to go back up to the top here and talk about something. So this omega is just 2 pi over t, but when I multiply it by the r, it gives me that tangential velocity. I do want to point that out. That's something we just covered in rotational kinematics. If you went back and watched all of those videos, you would already know that, and you're probably telling me that I did that wrong. But just remember that, again, our radial acceleration is just the 2 pi over t, and then the r gives us the radial version of that, right? Or the tangential version of that, but no big deal. Cool. Yeah. Cool. All right. So now let's cover the other two things I said I wanted to cover. But you didn't hear that because I skipped past all that stuff in the video. And I probably skipped past a lot of stuff. Don't worry, I talk to myself a lot while I'm putting these things together. Sorry. Cool. So, a couple things I want to cover. Tension on a line, and then we're going to cover gravitation real quickly. Okay? Cool. So, tension on a line. Let's say that I have a circle. I'm actually going to draw all of this out, and then I'll come back to the video. Okay? So, I'm going to draw all of this out, and I'll come back to the video. We're going to do this in 2 different ways, and we'll come back in just a second. Alright. Cool. So let's run through this whole thing that I just spent a few minutes doing. This is a lot of video, that's fine. So I want to do a couple things. First one I'm going to do is I'm going to take a rope and I'm going to spin it this way, and we're going to have a rope thing that's going on a weight in a vertical loop. The main thing to recognize here is that if I have a rope, that we know that the rope must be the reason why this thing is going in a circle. We know that, right? Because otherwise it would go the whatever direction I threw it, right? If I take a rock and I throw it, it's going to go the direction I throw it. Now it might curve, and that would be a centripetal force, but that's going to be due to gravity, and it's not going to make it go in a circle unless you're super strong and can throw that rock hard enough to go around the planet. Which I doubt. But the reason why this rock is going, or this weight that we have on this rope is going in a circle, is because the rope continues to make it go in a circle. So we can tell that this force of tension must supply some of it, what we're going to call radial force. Now, this is an example where force of tension is not the only radial force, and that force of tension's force does change. So we need to make sure that we recognize that, and that we see that when we start doing our problems. So to every location around this circle, we'd actually have a different combination of forces in terms of everything that makes up my sum total of radial forces. However, if I am going the same speed the entire time, my radial force remains constant, which I'm going to write here. Okay. So I'm going to show you my little example here. So let's say I have a weight, oh god, on a rope, and I'm spinning it in a circle. Now, I've just located here 2 different locations. One is at the very top of its arc, and one is at the very bottom. Now, my radial force is constant, right? Let's just say that it's 10 newtons. I'm going the same speed around the outside edge of this thing. Well, that doesn't mean that all of my forces stay the same. It just means my total force stays the same. Well, how can my total force stay the same but my radial forces differ? Or the forces that make that up differ? Well, in this case, my total radial force will remain constant because I'm going the same speed. But look at the very top of my arc. At the very top of my arc, gravity and tension pull both in towards that radius, right? They both help me out going towards that radius. So in that point, tension is actually going to be less. The force that's in the rope will be less than it will be at the bottom of the rope, because it doesn't have to supply as much of that constant radial force. Gravity is helping it. At the very bottom of this circle, we can see that in fact the opposite is true. The force of tension is going to be at its greatest, because not only does it have to supply all of the radial force, it also has to overcome gravity, which wants to pull this thing in the other direction. So we do have, when these things are spinning, a situation where radial force can be constant, right? I'm going the same speed, but the forces that make it up are not. So make sure that we recognize that if this is like a vertical circle, again, not horizontal, but vertical, that this thing would have these sort of makeups. So don't forget that. So let's take a look at this other example, which we worked with quite a bit. So let's say that we have something that's hanging from the ceiling, and you can see that it's spinning around this like green circle. Well, this force of tension, right, is going to be supplying this thing staying attached to the ceiling. But that force of tension, the direction of it, is not all in the direction of the circle that we're traveling. We only care about radial forces of forces that are in the direction that our circle is traveling, right, and along that radius. That doesn't mean that these forces don't have some effect, right? It just means that when we're calculating our radial force, we only care about that portion of it, right? Yes, these forces have some effect. Yes, we want the force of tension to be at this angle, otherwise we wouldn't be going in a circle.
right? If the force of tension was all up, this thing would just be hanging up and down. So in this case, just make sure we recognize that. So we have this force of tension that goes down along this line towards the object, but again, it's only the x portion of it here that goes in along the radius of this circle. So in this example, my radial force will be the force of tension x. So I have another piece set up for us here. Cool. So when we take a look at that, we can go back and solve for these pieces by using these pieces of information, right? So again, my force of tension x now makes the hypotenuse of a right triangle, and my force of tension makes the hypotenuse of a right triangle, and I can split that into these two pieces: force of tension y, which is going up, and force of tension x, which is going inward. Now, how do I know that? Why is force of tension y not pulling down? Well, because this weight is staying attached to the ceiling and it wants to fall, right? We know that gravity is on this object. So we know that force of tension y in this case must be canceling out the gravity. The ball is not accelerating up or down, therefore my y forces must cancel out. And because my y forces cancel out, that means again the force of tension y and the force of gravity are going to end up being the same. My force of tension x again here is my radial force, and I can solve for that because I have this right triangle, right? So in this case, think about what my angle is here for this triangle, right? We're talking about, in this case, this angle down here. And so because we have that angle down there, what does that make my force of tension x? Well, it makes it the adjacent side of that triangle, right? And because it's the adjacent side of the triangle, I can find that side by using the cosine of my angle. Now, again, how do we do that? Well, it's pretty simple. The force of tension x is simply going to be my force of tension times the cosine of my angle. Now, they'd have to provide that force of tension, but that's the idea. So they're telling us how hard is the rope pulling, but not how hard is the rope pulling in our x direction. That would be where we would go to find this. And again, that's a brief review of SOHCAHTOA. I'm not going to spend a lot of time on trig, since hopefully you have a pretty good grasp and review on that. I'm not going to do trig a bunch here. But again, we can go back and solve for this force of tension x. That force of tension x is my radial force. So if I find the force of tension x, I can always use that to go figure out things like how fast is this thing traveling and things like that. Cool. So remember, when we did these problems in class, the main thing eventually for us, which recognized in order to solve parts of this, was usually they didn't give us enough to just go ahead and plug for force of tension x. We had to solve for our force of tension, and usually we did that by knowing that our force of tension y canceled out the force of gravity, right? Because again, the force of tension y is force of tension times the sine of our angle. But if we don't know the force of tension, then that doesn't help us. But if we know that the force of tension y is the force of gravity, then we can easily go solve for the force of gravity, plug it in for the force of tension y, and then it'll help us solve for everything else. And that was some problems that we solved pretty frequently when we were going through the material. And if you covered that, you'll remember that it was part of the FRQ and that kind of stuff too. So things to look out for, because you know that there's a really good chance that they will show up. Cool. So let's talk about gravitation, and I'm going to try to do this quickly. Gravitation comes from a long line of scientists who were discovering that the Earth was not the center of the universe, right? You have ancient scientists, but I'm not going to cover all of those, that have some sort of idea on that. But for the most part, we're really talking about Copernicus, Kepler, and Newton. And Copernicus did observations that led him to saying that it doesn't make sense that people would think that the Earth was the center of the universe, that if you look at the way that planets orbit around Earth, they don't make sense in a circular orbit. They only make sense in a circular orbit around the sun. And then Kepler did measurements and figured out what the orbits of the planets were, and it had solid mathematical evidence that showed how they all fit in around the sun, and that helped people believe it more. And then Isaac Newton went through and found out his law of universal gravitation, and that showed essentially this varying force of gravity would give you the type of shapes that you would expect to see in the solar system. And then that was another way of confirming that these things really should be going around these large central bodies, the sun, things like that, and obviously us for the moon and things like that. So that's essentially the history behind gravitation. We're going to cover just the law of universal gravitation really quickly, and just making sure that we recognize that the law of universal gravitation gives us an additional centripetal force. I know I said we'd cover bank turns too. Bank turns are really easy. Bank turns, I don't think they're going to make you do a lot with it. But the idea, just remembering that if we have this contact force, it comes 90 degrees off the surface. So I actually do want to cover that. I just want to draw the picture really quickly. So let's cover a bank turn real quick. I know I probably should have done this in a different order, but you can watch this whatever order you want. You can
fast forward and just go to the gravitation stuff and then come back to this. It'll be fine. I'm trying to get this all done at one time, so cool. So let's say that we have a banked turn, like I'm going down a road that's at an angle, like I'm traveling down the road in that direction, and it's at an angle. So don't forget that we're going to have this normal force that comes off 90 degrees to the surface of the ramp. And let's say that it was completely wet out. There was no friction between me and the road at all, like completely wet. I would actually still have some force that would allow me to go around this curve, this bank turn, because I should have this portion of my normal force that comes off the ramp, right? So I would have this, what we're going to call the normal force, and then what we would call the normal force X. And again, it just means that the ramp, a portion of that ramp's contact with me is going to go in towards the circle. Now, if I did have friction, all we would do is just say one of those radial forces is probably also friction. And that's bank turns. It's pretty straightforward. It's just a way to make sure you recognize all pieces that go along with that. Okay. Universal gravitation. So the law of universal gravitation, again, it tells us what force to expect between two bodies. And this should be any two bodies. That's why it's called universal gravitation, right? So if I have an object, mass 1, and I have an object, mass 2, they will be exerting a force on each other. That is friction. They're both going to exert this force both ways. And so the law of universal gravitation tells me that I can expect to see a force between these two objects of the following. So we have the law of universal gravitation. The force of gravity between any two objects is this thing called the gravitational constant, which is a very small number, and it represents a way to say, how do I take this relationship I see to the right and translate it to the force I see? It's a good way to think about that. Right? It's the thing, big G, again, gravitational constant. The force that I expect to see between any two bodies is their masses multiplied over the distance between their centers squared. So again, what this tells us is that gravity is based on these two things, right? Gravity is based on how large is an object. The larger an object, the more gravitational force it will have between any other object, right? So two large objects are guaranteed to have more gravitational force between them than two small objects, given that they're the same distance apart. And distance, obviously, is the other thing here. We are inversely related to our distance, right? Inversely related to the square of our distance, to be specific. So our distance, as it gets bigger, the gravitational force goes down on us. And those are things that you would expect, right? Looking at the universe, you would say big objects have more gravity, objects that are far away put less gravitational force on us. And so that's the main idea there, is that there is this relationship, and again, this big G, this gravitational constant, which will be on your formula sheet, which make sure you print out, tells us how do I translate those relationships, right? So the main thing here is to recognize, this is probably the last thing I'll cover. I don't think there's much else that you need here. As in general, I would say go back and make sure you look at everything else. But yeah, so the main thing we have to cover here is that we actually have a radial force described by my force of gravity, right? If I go around the outside edge of the Earth, which is spherical or circular if you want to put it that way, because the path you travel would be a circle, then there is some force making me go around that circular path, which in this case is the force of gravity. That allows us to solve for a number of things, right? It means that I can literally say MAR is mg, in which case we can see that my radial acceleration is just 9.8 meters per second squared, right? Because if I cancel out the m's, which I can do because it's the masses of the same things, then it gives me radial acceleration is g, which is 9.8 meters per second squared. But more importantly, let's say that I wanted to know some other pieces of information about objects that are not the Earth, right? In this case, that g is 9.8 is we're using 9.8 even, which is a good estimation, but that's for acceleration around the Earth. That does change for different planets, right? So that would give you an idea of how to do that. But it allows us to do other things, right? So I know in this case that my radial acceleration, or my radial force, excuse me, is my force of gravity, which means that MAR is equal to mg, but mg is not the one we want to use here. We're going to use the other definition of force, which is m1 m2 over r squared. Okay. So we have now this other way we can set it up. MAR is equal to g times m1 m2 over r squared. Now when we say MAR here, we're saying, well, which object we're talking about? So let's just say that this was object 1. Cool. Well, that means that m1 is going to cancel on both sides, and that's going to give me another relatively easy formula to use. It's going to tell me that my radial acceleration is going to be equal to g m2
over r squared. Cool. Well, if AR is little g and AR is also this, then that means that little g, or our radial acceleration, is just gm2 over r squared. Cool. Well, what does that mean? Well, that means that if I can actually find 9.8 by plugging in my gravitational constant here, the mass of the Earth, and then the radius of the Earth to where I'm located. And that will actually give me 9.8, and that's how that's calculated. So that's one of those ways that we can set these things equal to each other. So let's go back and say the same thing, right? Exact same thing. It won't even take me that much longer. MAR is equal to G times M1 times M2. Now, again, the main thing here is that my M1s are both going to cancel. Cool. Because they're on both sides. And so that means that I can say, I have these two different definitions for, let me write this out and I'll skip past it. I have these two different definitions for my AR. Remember, we just covered that literally earlier in this video. And so I can go
B squared over R is equal to G M2 over R.
Cool. So I can do this with it. And these are things that we did do in class, so make sure you recognize this. So if my radial acceleration is g m squared over r squared, I can actually go back and set in what my radial acceleration is, which is velocity squared over r. And that allows me to solve for how fast is something going given this gravitational force. So if I have the gravitational force, I can figure out how fast that thing is going if I know the radius, obviously. And then I also can figure out what's the time period this thing is traveling based on its gravitational period, or its gravitational force. And again, that's just saying I had this other definition, this 4 pi squared r over t squared for my radial acceleration, and it gives me this period. Yeah, so pretty straightforward stuff. It's just another way of making sure that you recognize that we can set a bunch of formulae equally to each other. Remember, that was the entire point of this chapter. So yeah, hopefully, I know that's a ton of information. But yeah, that was a lot of stuff that we had in this chapter. Was just finding these different ways of describing which my circular force is and setting it equal to that definition, right? So that's the main thing. Make sure you recognize mv squared over r is my radial force equation, my radial force equation, and then everything else that I just covered, literally all of it, was a way of identifying what can I set equal to that? What actually represents that radial force, right? In some cases it's gravity, in some cases it's friction, in some cases it's tension, but we're just finding a way to set equal to that radial force equation, what is the actual named force that supplies that force? This is going to be a lot, I know that, but that's fine. I will cover, what do we have left? We have momentum and we have energy, and I'll cover those over the next couple of days. You can tell this video probably took me, it's 45 minutes now. You won't be 45 minutes to you, but it was a long video.